Okay, example 1. We want to find the flux of our force xyz, where S is defined as the surface z equals 1 minus x squared minus y squared, oriented upward, where z is greater than or equal to 0. So the first thing we want to do is sketch this, and that is just going to be your paraboloid, which looks like it opens down, and it's got to be greater than z equals 0, so it's going to hit the xy plane. So it looks like you're just going to have your basic paraboloid that seems like it does something like this, and then hits the xy plane, something like that. So what it says is we want to find the flux oriented upward. Upward in this case, and most of the time it's going to tell you outward. Outward, which means away from the center of... that does not even look like a word. Away from the center. Outward. There we go. Away from the center of your figure. So what's happening is you've got some kind of a force which is acting on this figure, and who knows exactly what the force looks like. It says XYZ, but what's happening is you've got some kind of a force which is, acting on this thing, and when it goes into this, what's happening as it comes out? We want this thing to be an outward, or in this case upward, orientation. So as the forces come up here and then they hit the side, they're going to start to go off at some kind of a angle. Now the force might go through straight up like this. But remember that what we're interested in is we're only interested in the components of the force that come off of the surface at a perpendicular, because that's everything that gets through. So what we're really interested in is all of the forces that come out of this surface in an upward orientation that are perpendicular. Whoops, that's backwards. That are perpendicular to the surface. That's all we're interested in. We don't want anything going down. It's not what we want, because it does say upward. So we want to make sure that everything is going up. All right, so let's take a look at all the pieces that we're going to have to figure out. First of all, we're going to have to parameterize it, because the surface does need to be parameterized. So we're going to have to do a double integral over S of f dot ds. But remember, what that's equal to is the double integral over d of f dot n, but n is ru cross rv dA, where this piece right here is our n vector. Okay? So let's go ahead and parameterize it. It is again, it's a paraboloid. It looks like the easiest thing to do here might be to use polar coordinates. So I'm going to parameterize this as x equals r cosine theta, y equals r sine theta, that takes care of the circular part of this thing, and z is going to equal 1 minus x squared minus y squared. So that's going to be 1 minus r squared cosine squared theta minus r squared sine squared theta. But hopefully you can see that if you factor out the negative r squared, you'll be left with a cosine squared plus sine squared. So really z is just going to equal 1 minus r squared. And this is going to be your r of r and theta. Those are going to be your variables here. So it's going to be r cosine theta, r sine theta, 1 minus r squared. And again, it's important that we write this in parameterized form. That way we can actually find out what the flux is. All right, so we're going to need to do the partials. So we're going to do r sub r. So let's see, the derivatives with respect to r are just going to be cosine theta, sine theta, and negative 2r. The derivatives with respect to theta are going to be negative r sine theta, r cosine theta, and then 0, because there's no thetas in that last entry at all. All right, so this is where things become important. Before, it didn't matter. If we did r sub r cross r sub theta or r sub theta cross r sub r, it didn't make any difference, because what we did after that was when we were doing the surface integrals, we took the magnitude. But now we're looking for the flux. We are looking specifically for the direction in this case, and we want this to be in an upwards direction. So what we're looking for is we are looking for a positive k value, or a positive z component. That's what we're looking for out of this. So when we cross these, the order will become important. What we are looking for is looking for a positive k, or a z component. So the order is going to matter, because we no longer have the magnitude to get rid of the negatives. So it is very important. Because it says it's upward, that means the k or the z components must be positive. Doesn't matter so much if the x's and y's are positive or negative, as long as the z part is positive. So we're just going to try it one way, and the good thing is there's an easy fix if we pick the wrong way. We're going to try r sub r cross r sub theta, and that only because that's the way I have it written right now. So if we cross r sub r and r sub theta, so let's see, if we get rid of the I row and column, I get 0 minus minus, so that's going to become plus 2r squared cosine theta. If I get rid of the j row and column, that's going to be 0 minus 2r squared, but we got to change that, so that'll become positive 2r squared sine theta. And then if we get rid of the k row and column, that's going to be r cosine squared minus minus r sine squared, which is plus r sine squared. So we get r cosine squared plus r sine squared, which hopefully you guys realize is just going to simplify to r without having to write that all out. And this is good. In this case, I do not have negative r, I have positive r. That's what we were looking for. Now, if it had happened to be that we picked the wrong way of crossing these things, which is fine, it just means that our perpendicular vector, our normal vector, because that's what we just found, would have been in the opposite direction. So if that was the case, all I would have to do is rewrite this, the cross product, and then change all of the signs. I could have rewritten it as r theta cross rr, and then changed all of the signs, and that would have worked out. In this case, however, we did pick the correct one in the correct order, so we're good there. Okay, so what we have just found is let's go ahead and highlight this in green. We found that piece right there. Okay. We already have our f function. F is, in this case, x, y, z. Now, it does need to be parameterized, so we're just going to replace x, y, and z with the x, the y, and the z that we found over here. So let's go ahead and take our double integral. Double integral over d of f parameterized, which is r cosine theta, r sine theta, 1 minus r squared, dotted with our cross product that we just found, 2r squared cosine theta, 2r squared sine theta, r dA. All right, we could fill in the bounds and everything right now if we want to, or we can go ahead and do the dot product, or you can do it all at the same time. I'm probably going to go ahead and put the bounds in here at the same time as doing the dot product. So let's see, I'm going to be dealing with r's and thetas. I know that, going back up to the top here, I know that r has to go from 0 to 1 because that is the biggest radius that I have here on this thing. And then it looks like this is going to be a complete circle, so theta is going to go from 0 to 2 pi. So let's go ahead and write that in. So we're going to have 0 to 2 pi for theta, 0 to 1 for r. Dotting these things, we're going to get 2r cubed cosine squared, 2r cubed cosine squared theta, plus 2r cubed sine squared theta. That's a good thing. And then plus r minus r cubed. and then we're going to have dr d theta. Notice we do not need to add an extra r in there. We do not need to put r dr d theta in there because we have already parameterized this thing. If we had not parameterized it, we would have needed to put an extra r in there, but it's already parameterized, so we don't need the extra conversion factor of an r there. So just be careful not to add that in there. So this right here is good because if I factor out the 2r cubed, I'm going to get a cosine squared plus sine squared, which is 1. This is going to be very common in all these problems. So that's going to leave us with an integral from 0 to 2 pi, integral from 0 to 1. The part in blue there just simplifies to 2r cubed plus r minus r cubed, that is supposed to be a cube, minus r cubed dr d theta. And the good thing is there's no theta, so we can separate that. 0 to 2 pi of d theta times 0 to 1. And I've got 2r cubed minus r cubed, so that's going to give me an r cubed plus r dr. So the antiderivative or integral from 0 to 2 pi of d theta we have done so many times now, that's just 2 pi. We do have to do a little work on the other one, so that's going to be 1/4 r to the 4th plus 1/2 r squared from 0 to 1. Let's go ahead and plug this stuff in now. If I plug in 1, we get a 4th. If I plug in a 1 to the other one, I also get a 1/2. If I plug in 0, I get nothing. So it looks like I'm going to get 2 pi. A 4th plus a 1/2 is going to be 3/4. So multiplying this out, we're going to get 6 pi over 4, but that reduces to 3 pi over 2. That is the flux. In this case, it is a positive flux value. That just means that when we go back up here, the amount of stuff passing through this, this paraboloid surface is positive. The amount of stuff that's coming out has a positive flux. More is coming out of this surface than is going into or staying parallel to the surface. All right, example 2, it says find the flux of F, which is defined to be a 0, 0, z, across the outwardly oriented surface x squared plus y squared plus z squared equals a squared. Hopefully you recognize that surface as just being a sphere. Whoops, probably too big. Let's just try and sketch the sphere. So, easiest way for me to do it is to just draw the circle. That is an awful circle. Let's try again. A little bit better. All right, and now we've got this part coming around here. And the back part's dotted. Now we got the part coming down this way. And then dotted there. So we've got our sphere centered at the origin. It's got a radius of a. All right. And let's see, it says we want to find the flux. Now it says that the flux is 0, 0, z. So you can actually figure out what this force field looks like. I'm sorry, it doesn't say the flux is 0, 0, z. It says the force is 0, 0, z. Well, it just means that the force is going to be dependent upon z only. It's got no x or y direction, so the force is completely vertical. If z is positive, if you have a positive z, that means your forces inside of here are heading straight up. And obviously, the higher z is, the bigger the force is. So the closer we get to the xy plane here, the smaller these are going to be. The further we get away, the longer they're going to be. And then if you have a negative z, that means that, again, the forces right to here are going to be straight down. And the further you move away, the longer they will be, because the greater the z, the greater the force is going to be. And that's good, because that means that everything is going to be out. It's going to be outwardly oriented of this sphere. So when it hits the sphere, again, what we're interested in is while it's going to be hitting the sphere going straight up and down, there's going to be a component coming out of the sphere at every single point, which is perpendicular to the sphere. And that's what we're looking for. Those are the pieces that we're looking for. So in order to do this, to figure out the flux, again, what we're going to need is we're going to need the force parameterized. Okay, we can do that pretty easily. And we're also going to need the cross product. Well, this is spherical, so it makes perfect sense to use spherical coordinates here. Let's go ahead and parameterize x as, in this case, the surface of this thing. Remember, it's not everything on the inside, it's only at the surface. The surface of this thing, the rho value is a, and then it's sine phi cosine theta. Y is going to be a sine phi sine theta, and then z is just a cosine phi. All right, so that gives us our r of phi and theta, which is going to be a sine phi cosine theta, a sine phi sine theta, and a cosine phi. Okay, we're going to need the partials. This is all just to find n. We already have our parameterized, or we already have our parameters. We'll be able to parameterize the force when we need to do the dot product. So we'll need our partial with respect to phi. And that's going to be, let's see, with respect to phi, that's going to be a cosine phi cosine theta, with respect to phi, there's something wrong there. No, it's not. A cosine phi sine theta, and then negative a sine phi. Yeah, that looks right. Okay, and then we'll do this with respect to theta. With respect to theta, we get negative a sine phi sine theta. With respect to theta, the second part is going to be a sine phi cosine theta, and there's no theta in the last one, so we just get 0. Okay, so now we need to find our normal vector, and our normal vector is the cross. And remember, if we don't get the right one, we can always just switch the order and switch the signs. We're looking for outward orientation, which basically means that the z component here has to be positive. Okay, so let's see. Crossing the first one, so if we eliminate the I, row, and column, we are going to get 0 minus minus, so it's plus a sine squared phi cosine theta. If we eliminate the j, row, and column, we're going to get 0 minus a squared, oops, I should have a square on this first one, so a squared sine squared phi sine theta. Be very careful on these and try to keep this straight. Does that look right? 0 minus, but I have to change the minus to a plus. Okay, so that's correct. Okay, and then the last one, if I eliminate the k, row, and column, it's going to be a little bit longer. I'm going to have a squared, let's see, sine phi cosine phi cosine squared theta, minus minus or plus a squared sine phi cosine phi sine squared theta. Okay, yeah, that looks right. Okay, I think we're good. All right, hopefully what you see here is that in this last piece I've got a squared sine phi cosine phi, a squared sine phi cosine phi, and what I have left over is a cosine squared plus sine squared of theta. That is a good thing because that's just going to give you that 1, so we're basically going to get rid of the cosine squared and the sine squared of theta. All right, but what you should also notice is that within every term I have a squared sine squared phi. I'm sorry, a squared sine phi, a squared sine phi, a squared sine phi. I'm going to have one of those in everything. So I'm going to go ahead and take an a squared sine phi out to the front. It's just going to make doing the dot product a little bit easier later on. You don't have to do this step that I'm doing right here. It just makes it a little bit easier for the dot. Okay, so let's see. A squared sine phi. If I take that out, that's going to leave me with cosine theta, sine theta, and then what is that going to leave us with? That's going to leave us with a cosine, yeah, cosine phi. Does that look right? No, something's not right. Oh, I didn't write the first two correctly. I'm only taking one of the signs out, so I'm going to still be left with a sine phi cosine theta. And then I'm going to be left with a sine phi sine theta. Yeah, there we go. And then the last one I am just going to be left with a cosine phi. Now I did do a couple of steps in one at one time between that one and the one I just did here in blue. So hopefully you're okay with seeing that. Okay, and then I need to parameterize. So we need to parameterize f. Now f is just 0, 0, z, so that's just going to be 0, 0, a cosine phi. So our f function, let's go ahead and write that down here. The f function parameterized is going to be 0, 0, and then a cosine phi. All right, so now I need to dot, because what we just found here was our normal vector. We need to dot f with n. Well, the good thing is dotting these, this is going to be really nice. I've got 0 times something, 0 times something. The only thing that gives me anything is the k components or the z components here. So my dot product is going to be pretty nice. So we've got f dot n, which is going to be a squared sine phi. That's from the outside, can't lose that. And then we've got 0 plus 0 plus a, cosine phi. So really what I'm going to get is, it looks like a cubed sine phi cosine phi, if I'm not mistaken. Something doesn't look right there. Oh, should be cosine squared. Multiplied the cosine times the cosine. Right, there we go. All right, so let's go ahead and take a look at this. We're going to go ahead and take the double integral over d of a cubed sine phi cosine squared phi and dA, which is going to be, let's see, what do we have here? We've got phi and theta, because it's spherical. Remember, a was constant, so we don't have to worry about the rho part. All right, so let's go ahead and figure this thing out. So we're going to have 0 to 2 pi and 0 to pi. That's for theta, and that's for phi. Let's pull the a cubed out to the front. Sine phi cosine squared phi d phi d theta. Well, I have nothing with theta in it, so we can separate these. So we have a cubed integral 0 to 2 pi of d theta times the integral from 0 to pi of sine phi cosine squared phi d phi. All right, the integral from 0 to 2 pi of d theta, again, we've done that several times, so that should be no problem. So we're going to have a cubed times 2 pi. Now we are going to have to do a substitution. So we're going to let u equal cosine of phi, which means that du is going to be negative sine of phi d phi. And so d phi is going to be du over negative sine of phi. And we'll go ahead and change the bounds. So if I plug in 0, we're going to get 1. If I plug in pi, we'll get negative 1. The fact that those are upside down won't really matter much because I think we're going to get a negative. Whoops, I actually lost my negative up here. Hopefully you caught that. All right, so we'll have sine of phi u squared times our new d phi, which is du, over negative sine phi. The sine phi's are going to go away. The negative will flip the bounds. So over here we have 2a cubed pi. Don't lose that. 2a cubed pi times the integral from negative 1 to 1 of u squared du. Okay, and the bounds flip because of the negative sign attached to the negative sine phi in the denominator. So let's go ahead and finish this off. We get 2a cubed pi times 1/3 u cubed from negative 1 to 1. So 2a cubed pi. Plugging in a 1, we get 1/3. Minus plugging in negative 1, we get negative 1/3. So that's going to give us 2/3 on the inside. Multiplying that by the 2a cubed pi, we get 4a cubed pi over 3. And that is the flux coming out of this sphere given the force 0, 0, z.